Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and today's video is on the nearest neighbors algorithm for supervised machine learning. I'm teaching it as part of a course called Analytic Methods for Lawyers. The fundamental idea behind nearest neighbors is really simple. Things behave similarly to the way similar things behave. In other words, in order to do prediction, all we really need is some kind of similarity metric so that we can say that case A is similar to case B, or house A is similar to house B. And what we do is we find the neighbors, we see what targets they have, and then we basically aggregate those targets, aggregate the outcomes of the cases, aggregate the prices of the home, aggregate the survival of whether someone lived or died on the Titanic, and we make a prediction basically that is predicated on that aggregation. Now, yes, we can add in bells and whistles so that maybe we weight our closer neighbors more than the more distant neighbors, and we have to consider how many neighbors to choose. But nearest neighbors ends up working remarkably well, provided you can find a sensible similarity metric. The other virtue of the nearest neighbors algorithm is that you can actually, once it is constructed, explain to someone why the machine made a particular decision in a particular case. Or at least you can do so if the person hearing you doesn't ask too many questions. Okay, let me take a very simple example. We're going to have 100 data points, and there's just going to be one feature, which is a number, and one target, which is likewise going to be a number. So to generate the features, I'm just going to seed a random number generator. Let's get out of this because I ran a little bit of code before when I was just playing with stuff. Okay. Let's seed a random number generator. We're going to generate our features. They're going to be values between 0 and 12. There'll be 100 of them. I'll call that x. And now our true function, what we're trying to get at before all the noise is added in, is just an additive sine functions. They have different amplitudes and different periods, but they're just a couple of sine functions added together. Here's our noise function. It says take whatever you got and add some normally distributed noise to it. So to get the target values, I compose our not noisy function with our noisy function and map that over the values of x, over our features, and there we go. Okay, now I'm going to create a function here. After I evaluate this nearest thing is going to take our data x, ignore what the all is for right now, and it's going to produce something called a nearest function. What that nearest function will do is it will then take any point P and it will return information about the points in X that are closest to P. What is this all doing? This all says I want to know what the point is. I want to know where in my list of points it lies, the index into the points, and I'd actually like to know how far my point is from that particular point. So let's execute this. This is one of the slickest and most powerful functions, I think, in the Wolfram language, nearest, and there we go. So it produces something called a nearest function object, and here's what I can do. I can say, all right, I'm curious about 0.8. Let's see which values in x are closest. And so if I do that, it says, okay, it's element 10. It has a value of 0.82. That is quite close. And here's the distance to it. In fact, I can not just use a single point. I can use multiple points. I could use map, but I don't need to. It automatically threads because nearest functions have a attribute called listability, which means that you don't have to use map if you don't want to. But you can see, look, here's our point that's closest to 0.8, and here's our point that's closest to 1.3, has a value of 1.249. It's the 14th points in our list, and here's how far it lies away from our 1.3. Okay. Now, the nearest neighbors algorithm is often called K nearest neighbors, or it's often abbreviated as KNN. What's the K? The K is the number of neighbors you want to look at. And as far as I can figure out, it's always K. It's never M, it's never J, it's the K nearest neighbors. So by adding a second argument to our nearest function, I can specify the number of neighbors that I want to see. I want to find now the 3 closest neighbors to 0.8, and here they are. It's going to tell me their index and their values and how far away they are. So I could also then take these return values, and then here's what I'm going to do. I'm going to say, get me the index values out. So that's going to get me 10, 11, and 9. And then I'm going to say, take my targets and find the 10, 11th, and 9th parts of them. And that's going to give me the target values associated with the 3 nearest neighbors of 0.8. I would say this might be the most important piece of code in this lesson. Here's the idea again. You take your neighbors, you figure out what positions they occupy in the list, and then you take the same positions in the target and get the values of the target associated with the neighbors. So let's run that. There are our target values. And now if I can aggregate those and say, well, probably the best we can make is the mean. So I just add mean to our postfix pipeline here, and I now have a prediction for what the value of the function is at 0.8. I didn't really use any formulas. I just said, hey, who's nearby? What'd they do? I found out what they did, and I said, well, I'll take the average of that. Okay, we can turn this process into a function. Here it is. I'm just really copying the code down. The only bell and whistle I'm adding is I'm saying, well, I don't want to restrict myself to aggregation by mean. Maybe I want the median. Maybe I want the max. Maybe the targets aren't numeric and I need to process them in some different way, as we'll see later when we look at the Titanic. So here's the code. It's basically saying what nearest neighbor does is it's going to take the target values. Here's our nearest function that we've constructed. Here's our number of nearest neighbors. By default, that's 3. Here is the aggregation function. By default, that's a mean. And then when you apply it to some value x, you get out basically what we got out here. And so we can just verify that this works by using nearest neighbor predictor of y and nf. K has a default of 3, G has a default of mean, and apply it to 0.8, and we get the same answer, so that our function works. Let me note sort of a philosophical point, which is that there's nothing really resembling a conventional function that results from a nearest neighbor's predictor. You can't say, like with logistic regression, well, you take 0.3 and you add twice the feature value, and then you take the logit of that, and that's your predictor or something. There's no formula. Instead, you kind of reason by analogy. For example, instead of saying, the outcome of a legal case should depend on the following decision tree. You know, was it in commerce? And is it something that's been done historically? And that's often how legal rules are stated, particularly, I might add, in reductionist, oversimplified horn books that I don't like. But instead, what we're going to do is we're going to directly reason by analogy. We're going to need some explicit or implicit theory of similarity among cases. And we say that the closest cases to ours are some set. And we then do on our own case what most of the cases that we deem similar, those are called precedents, did. And there's no real mediating rule. All we have is a similarity metric. Now, that similarity metric might have itself a rule embedded in it, but still, it's kind of a different way of reasoning, and it's something that I think courts instinctively mix and match with more traditional decision trees. All right, back from the philosophical implications of the nearest algorithm for jurisprudence and on to some code. So, one thing we could do now is we could plot our true function. So this is kind of what we're aiming for. I'm not going to show it to you yet because I'm going to show it to you in conjunction with our predicted function. So here's what we're going to do. Here's our data points. This is going to get our data points. This is the true denoised function that we're kind of hoping to find. Maybe symbolic regression would find it. You could test that on your own. Or you can't because you don't have access to the package. But if you did, you could. And then here's what our nearest neighbor algorithm is predicting. And let's put those together. And we can see the blue dots are the actual data points. The purple line is the true function that we're trying to guess. And the red line is what our nearest neighbor predictor is saying. And it's by no means perfect. Like right there, it's finding sort of a possibly false dip in the function. But it's not bad. And I would say, in some sense, the data is really quite noisy here. Look at this, it's a mess. And yet somehow it's intuiting something that's fairly close to the real function. Let's see how our predictor does, though, on data it's never seen before. I'm going to generate the data using the same algorithm as before, just a different seed to our random number generator. I'll do the mapping of the composition of not noisy and noisy onto our test data. And then I'm going to use predictor measurements. What I'm going to do is I'm going to get the predicted values by mapping the nearest neighbor predictor based on y and our nearest function over the test data. And I'll compare that to the true targets, which are in y test. So if we run that, this is what we get. We get an r squared of 0.586, and it's not so bad. You can see it's sort of tracking. I think, honestly, it's the reason it's struggling is that the data is very difficult to match. There's a lot of noise in this data relative to the signal. It's time for a new concept. I could have taught you this concept earlier, probably would have been fine. But I think it's helpful to sort of have the basics of machine learning under your belt and have some experience with it before we get into the idea of a validation set. Okay. You'll notice that there was a parameter that we needed in order to make the nearest neighbor algorithm work. I needed to specify how many neighbors we were going to look at. Was it 3? Was it 5? Was it 7? Was it 1? And that parameter might well affect the predictions in individual cases, as well as the overall success of the nearest neighbor's algorithm. And in fact, although I didn't emphasize it perhaps all that much, we've seen parameters before, like how many trees are in a random forest, or what's the maximum leaf size in a decision tree. Now, what a good machine learning algorithm tries to do is it tries to figure out, based on the data in front of it, what would be the optimal parameters. But how can it do that? It can't access the test data to see which number of trees or which number of neighbors would result in the test data fitting best. That is called cheating, right? You're not supposed to look at the test data, otherwise it's not really test data, and it would lead to overfitting. But if you use the training data to try to calibrate the machine learning system, then you're kind of cheating too, because again, you're customizing the parameters for the entire data set. And so what you'd really like to have is some extra test data that you could play around with. And you could then see, did 5 neighbors work best on this play data, or 9 neighbors work best on this play data? But if you had so much play data, you would use it for training. You wouldn't, we don't have lots of play data usually lying around. So what's the solution? The solution is a compromise, and it's called a validation set. The idea is, okay, I'm going to sacrifice some of my training data. I'm going to give it up and not use it for training, and instead I'm going to use it to validate the parameters that I should be using to conduct the training. And by the way, those parameters are sometimes called hyperparameters. But either way, the idea of the validation set is to let you optimize the hyperparameters. Now, there's a trade-off here, though. The more data you use for validation, the less data that's fresh to be used for training. And so you have to make some choices here. 10, 20% is often not an unreasonable choice for validation. If you have a lot of training data, then you may be able to get away with using a higher fraction for validation because you're still going to have enough data left over to do some decent training. But that's the idea of a validation set, and it's something that good machine learning algorithms are going to either grab on their own or ask you to tell them about. So let's hand tune our own nearest neighbor algorithm. And let's first just do it visually. I'm going to do everything that I did before, but instead of using 3 neighbors, as I did before, let's use 5 neighbors and just see what our plot looks like. We'll eyeball it. Does it look better or worse? And I'm thinking it looks a little bit better with 5 neighbors. It's sort of smooth. With 5 neighbors, you're sort of smoothing out the noise. And so if you don't have a lot of very localized variation here, then in your target value, then 5 neighbors in this instance might be better than 3. Well, if 5 is better than 3, maybe 15 is better than 5. Let's see if that's true. And I would say this is suggesting it's not true. Yes, we're getting the gross features of the true function, but we're missing lots of local variation in the true function because we're just looking at neighbors that are too far away. And so we may have a Goldilocks principle going on here, that you don't want too few neighbors because then you're going to chase noise and sort of pursue false localized structures. On the other hand, if you have too many neighbors, yeah, you're going to average out noise, so that won't be a problem, but you're going to miss sort of localized information. Well, we can scientifically assess what level of neighbors is, what number of neighbors is best. Here's what I'm going to do, and this code, as I note in the essay, is really more than I need you to understand, but I'm just going to kind of give you the basic idea here. We're going to split our data into a true training and a validation set by use of this take drop command, and f is going to be the fraction of data in the true training, and 1 minus f will be the fraction of data in the validation set. And then what I'm going to do is I'm going to produce 20 true training validation splits of the data by using 20 different random seeds in order to come up with different splits each time. And every time I'm going to be using 20% of the data for validation. I'm not going to change that. What I'm just going to change is which particular pieces of data go into the true training set and which are going to go into the validation set. So I'll do that. Then what I'm going to do is I'm going to train the nearest neighbors predictor on the training data. So I'm going to find the nearest function using the training data. I'm going to see how we perform, or what it does on the validation data. I'll compare that with the validation targets, and I'll develop an R squared. And for what values of k will I do this? I'll do this for the values of k in k range, which by default is 1 to 15. All right, so that's going to give us a table. This code is now what's actually going to take the time. I'm going to generate 20 different R squared values on the underlying training data. And so I'm going to run this. As I recall, it takes about a minute or two to run, and so I'll probably pause the video and resume afterwards. Here we go. All right, it started. Okay, that did take a while, but we're back. And you can see we've got, on this first set when k was 1, the R squared was negative 0.004. On this set when k was 11, the R squared was a horrible negative 0.11. And now all we're going to do is we're going to use MapReduce operator to say for each k value, we're going to group by the k values, find out all the R2 values, take the mean of that. So we do that, and we've got our means, and now let's plot that. Again, you don't need to understand the key value map business, but what you can see is that as it looks to me like for neighbors seems to produce the best result. As we get a lot of neighbors in, it starts to get, it's just doing worse than actually just picking the mean value all the time. But hopefully our calibration mechanism would come up with some number of neighbors in the 2 to 6 zone. It might not hit exactly 4, but at least hopefully it wouldn't be picking like 13. All right, that's a basic nearest neighbors algorithm that I've home brewed. Let's talk about one variation of that, which is to weight the votes of the neighbors by how close they are to the point. That is, in the system I had before, all neighbors were equal. And maybe that's legit, but I think we would have reason to think that neighbors that were closer to a given point would be more similar than even neighbors that were more different. So that's what this code here is going to implement. It's similar to the code before. The difference is that what we're going to do is we're going to take the dot product of the weights of the neighbors with their values. Okay, that's the concept being implemented here. What are the weights? The weights are an exponential decay of their distance. So that, remember that if I do x to the negative 0.5 t, and I plot that as t goes, and probably t is not the best variable. Let's call it d for distance. I'll get something that goes, it starts at 1 if they're right on top, and then it declines, so that by the time they're 10 things away, they don't count very much. Supposing I were to say one of my points is 1 unit away and the other is 2 units away and the other is 3 units away, then I would get those as my weights, and of course I would want the weights to sum to 1, so I could just do our friendly normalize by total thing that we've done before, and we would then get the weights to be associated with each point. And that is really what I've done in this code here. That's this business here. So if I do the weighted thing, I get a slightly different result than I did before. I can turn this code into a function in that lovely way that Wolfram language works, where first you do a concrete example and then you figure out how to abstract from it. Our arguments are similar to what they were before, except that we have a decay factor here of gamma, which by default is 1. That's that 0.5 thing I used here, but we could use whatever decay factor we wanted. So if we have a high decay factor, we're really going to focus on points that are close to us. If we have a low decay factor, then we're going to treat the points more equally to each other. And this really is the identical code as above. The only real difference is I've taken 0.5 and I've plugged in gamma. So what I could now do is I could now plot the weighted nearest neighbors, the function that it finds depending on what the decay factor is. And I'll hold the number of neighbors here constant at 7. I probably should have used 5, but let's just stick with 7. And what you can see is that the decay factor makes a difference. And by the way, isn't that pretty? When the decay factor is 4, we are really nailing this function with 7 neighbors. So just another little bell and whistle on the nearest neighbors algorithm is to use weighted distances. So far I just used one-dimensional data for nearest neighbors, but of course we want to be able to use this algorithm for multi-dimensional data. Let's just see how that works. And by the way, in the course of using multi-dimensional data, we're going to spot an issue that we're going to have to figure out how to resolve. All right, see our good old random number generator, generate 500 two-dimensional points, each value of which ranges from 0 to 12. Create our true function, our not noisy function, add in some noise, and then get the targets out. All right, so we've got our targets, which we'll call Z. Here's what we're trying to get. This is our goal, and I guess I suppressed printing it out, but now let's print out our goal and see where our points are relative to that goal. And there's some noise there, but this is what we're trying to come up with a predictor. This green surface is what we're trying to emulate. All right, we're going to do it the same way we did before. We're going to take for those points x, y that I defined above, and we'll create a nearest function so that if I give it a new xy point, it will find me the nearest value. So for example, if I take NF2, which is what we just computed here, and I apply it to the point 5,7, I learned that the closest point to that in the xy set is actually at 5.13, 7.00. That happens to be the 221st point in my set, and it lies at a distance of 0.129. Okay? I can then make a predictor out of this. I could say, take our targets, take our nearest function, take our data point 5,7, and let's see what we predict the value of our function will be at 5,7. And it says that it's negative 0.331. Okay, so now that we know that nearest neighbor predictor, when used with the targets, the new nearest function, and a point, produces a prediction, we can exploit that, and we can actually plot what our predicted surface looks like as x goes from 0 to 12 and y goes from 0 to 12, and we'll compare that using show to what our true function should look like. And so the green function is the true function, and the red function is our nearest neighbors thing. You can see that nearest neighbors thing has a lot of sort of local choppiness to it, but and we can look underneath it. But it's okay, not terrible, not great. All right. One thing we could also do is, instead of using the default number of neighbors, which are 3, we could use 7 neighbors, which maybe would work better. All right, and does it work better? Maybe a little bit. However, perhaps there's a problem here. My distance function, by which I concluded what points were equally distant, assumed the scaling on the x-axis was the same as the scaling on the y-axis. It was just computing the Euclidean, it was using the Pythagorean theorem to figure out the distance between 2 points. But what if the points on the x-axis are in millimeters and the points on y-axis are in centimeters? Well, the x numbers are going to be a lot bigger, generally speaking, than the y numbers, and so x difference is going to dominate y difference, and that may not be at all what we want. So how do we basically normalize the data so that differences in units don't matter? Well, there are 2 basic ways to do it. One is to change the nearest function, and the other is to change the data. Probably they're equivalent at some level, but I think there's one that's a little bit easier. I'm going to show you probably the harder one first, which is to come up with a custom distance function. And here, the idea is instead of using the Euclidean distance, I'm basically going to take 10 times the difference of the x values and just 1 times the difference of the y values. And have I done it backwards? I believe that if the x-axis is millimeters and the y-axis is centimeters, then what I want to do is I actually want to do the reverse of this. Hopefully this will not massively screw up everything I've done before. All right, and now I can compare whether the points that are now nearest to 5, 7 under the old nearest function are the same as the points nearest 5, 7 under the new nearest function. And you can see that, well, 221 wins out both times, but other than that, there are differences. And from here on in, all our code stays the same. We can come up with a nearest neighbor prediction. We can compare our true function to what our new scaled nearest neighbor predictor has developed. And that's what you get. Okay, that maybe works okay where all the data is numeric. But what if, for example, some of the data is categorical? Then what do we do? Let's raise the Titanic and see. So I'm getting our Titanic data, and the only thing I'm doing a little differently from before is for this lecture, I don't want to deal with missing values. There are cases where we don't know what age somebody was and the like. I'm just saying if there's any missing data, just get rid of that row. We'll have enough rows. All right, I could write a custom distance function again, right? I could say, look, remember what a sample passenger looks like? Let's look at a sample passenger here. Titanic training. Our first passenger. All right, it's a first class 29-year-old female who happened to have survived. Mostly what I'm going to be dealing with is only the features. So that's what the features looks like. So here's what I could say, perhaps. I could say, look, if the first attribute of the first passenger is different from the first attribute of the second passenger, add a point. Otherwise, add 0. And if the gender of the first passenger is different from the gender of the second passenger, then also add 1. Otherwise, add 0. And then take 1/10 of the absolute value of their difference in ages. And that's some metric of their distance. It has the general virtues of a distance function of giving positive, non-negative values. It's symmetric between passenger 1 and passenger 2. And so there you go. And now I could say, could you please compute a nearest function using the Titanic training data and using my custom distance function. I'm going to set the distance function option to passenger distance, which I created up there. And now we can actually make sure this works. Let's see who it thinks the nearest neighbor is to our hypothetical hero, the first class 63-year-old male. And it turns out to be other males of similar ages who also were in first class. So how do we predict how our first class 63-year-old male is going to fare? We're going to make use of a function called commonest. Commonest just takes a list and it returns the most frequently found value. It wraps it in the list. Why is it wrapping it in the list? It's because there's the possibility of a tie. What does it do in the event of ties? It's going to list both of them, but sort that list with respect to the first value that it encountered. So in the first one here, it first encountered died, so died comes first. And in this commonest, it encountered survived first, so survived comes first. In any event, I'm going to try to avoid, I'm going to try and show you how to use nearest neighbor predictors with, instead of using mean as the aggregation function, I'm just going to take the first value of the commonest. And Is that vulnerable to arbitrary tie breaking? Yes, but this is pedagogic, not industrial. All right, and we'll do it for our first class 63-year-old female and for our third class 24-year-old female. And I'm afraid they both died. All right. So, what if I make her 28? They both died. Okay. Let's just look at something here. I was wondering why that woman survived, but it's because she's in third class. Let's upgrade her. Yay, she survives. Okay, the other thing I could do rather than getting a single prediction is I could get probabilities. That would be nice. And the way I could get probabilities is just looking what fraction of my neighbors survived and what fraction died. To implement that, I'm going to use the item counts resource function, which is kind of like counts, except you specify what the keys of the association are that you want to see. And then that'll give you raw numbers. I want to normalize them so that it's more like a probability distribution where the elements sum to 1. And so, with respect to our first class 63-year-old male, it's bad news. 100% of the 3 died. With respect to our third class 24-year-old female, there's a glimmer of hope as one of those women, or one of the neighbors, survived. Okay, so that's how you could do it. The problem with this approach, though, is it requires writing a custom distance function. And while that wasn't so hard when I just had, whatever it was, 3 features, imagine a data set that has 100 features. That could be a nuisance. Moreover, it's a little bit arbitrary. I mean, I said that age differences, I would weight them at 1/10, but why? Why not have them be 3/10? So there's another way of doing it, which is to change the data. And Wolfram has an automated way of dealing with the data so that basically all of the data sort of counts equally. And the function that we need to do this is called feature extraction. And we run feature extraction on the features that we are trying to get information on, and it's going to create a feature extractor function. And we can then take our feature extractor function. This is a 2-step process. First we create the function, then we apply the function to our data. So let's see what our feature extractor function applied to our hero is. And we get a vector of numbers, of 6 numbers. Why 6? I believe it's because, well, one of them is encoding age. It sort of takes 2, or you can use 2 to encode gender, because we didn't have non-binary gender back then, and sort of takes 3 values to encode cabin class. Maybe some of you are thinking you could compress that a little bit. That's true, but it's not doing maximum compression here. All right, so what we can then do is take our feature extraction function, run it on our Titanic training data, and then for each column, that's what array reduce with a last argument of 1 is going to operate on, compute the mean and variance of each column. So what we're doing is we're saying, what is the mean and variance of each column of the transformed training data? And essentially the mean is always a 0, and the variance is very, very close to 1. And that's the goal. That means that if we use Euclidean distance now as the metric, everything's kind of been scaled properly. It's all operating on the same scale. And so I can now run nearest. I don't have any custom distance function, but I've changed the data by using a feature extraction function to normalize it. And I get a new nearest function. And now, if I run that new nearest function and I ask for the 5 nearest neighbors of our FEF encoded hero, this is what I get. I could see what happened to those people. Let's get, these are the targets of our training data. And now let's get the values of the target for the index number of my 5 neighbors, and it's bad news, isn't it? They're all dead. All right, maybe we could look at probabilities, and it's 100% dead. All right, let's see how my home-brewed nearest neighbor classifier does on the Titanic data. We're going to develop the Titanic training thing on the training data, no peeking. And then, having done that, right up to there, come on, there we go. Here's what our home-brewed classifier predicts, or classifies as. Here's the true targets, and let's see how we did. Pretty well, 81.2% accuracy relative to a baseline guess of 61.1% if we just guessed everybody dies, like they do on House episodes. All right, so I did pretty darn well. We could compare that, and I'm not sure what happened to that little piece of code, but let's compare it to what the out-of-the-box method does. So let's classify our Titanic training data using the nearest neighbors methodology, and we're going to calibrate that check that on the test data. And when we do that, come on, little thing, do your thing. Go, go, go. I should have put training progress reporting goes to none. Be patient. If this were a live class, this is when I would ask whether anyone had any questions, but no such opportunities here. But we're done, and its accuracy was 80.6%, and so I did at least as well. Arguably, I beat it. All right. So that's a home-brewed nearest neighbors algorithm, and I just compared it quickly with the out-of-the-box method. And I guess I sort of jumped the gun here because it's out-of-the-box method that I want to talk about next. The good news, as usual, is now that you understand the concept, the implementation in Wolfram language is pretty easy. We just use, if we're doing a prediction task, we just say predict, and we just set the method to nearest neighbors. We're done. Just like, remember, random forest had sub-options where you could tell it how many trees you wanted. Well, here we could say how many neighbors do I want, and this is the code format here. You just wrap up method in the list. The first part of the list is the method you want, and then you set various options. You can also use nearest neighbors for classification, as we did on the Titanic. You can find out, by the way, information on, hey, what did the out-of-the-box method do? How many neighbors did it use? It used 20 neighbors. And you could also figure out, hey, I wonder what it did for feature extraction, because it had to do some feature extraction. And so it looks like it did feature extraction after figuring out that the first and third variables, namely cabin class and gender, were nominal, which is a synonym for categorical, whereas age was a numerical vector. And as I noted earlier, I think we're going to get the same value here, yes, that I actually end up doing a tiny bit better than the built-in method. A code note before we conclude. Nearest neighbors does take up a lot of memory because this storage of who's next to whom and what their values are, that can take up some space. And so I wanted to show you here how the amount of memory a nearest function took varied as we varied the number of rows and as we varied the number of columns in the data set. So I'll run that. Byte count is just measuring memory usage, and you can see that it scales pretty linearly. But by the time I'm at 100,000 rows and 1,000 features, I am using 800 megabytes worth of data, which is doable on a modern computer, but you do have to have some concerns. What about how long does it take to get the nearest information? And here I'm basically going to do a similar experiment. I'm going to use repeated timing. I think I've used this before. The idea is the first time you run code, it can be slow, and that's a little bit of an unfair estimate. So repeated timing takes an average, and we'll do this. And I don't think it's going to take that long. I think we're almost done, and we're getting very close. And now we're there. All right. So even with 100,000 rows and 1,000 columns, on average, it just takes a second to build our nearest. Nearest is a very slick, well-done function. So it's doable. It's just something that you want to be aware of. Although, as we'll see, big neural networks just make this nearest neighbor stuff look tiny. So what do we conclude about nearest neighbors? It is a strong algorithm for classification and prediction. It often is very accurate, and it produces interpretable results. We are not releasing you from prison because 9 out of the 10 people similar to you, using our similarity metric that we're not going to tell you about, that we did release went on to recidivate. Now, there may be some privacy concerns when that person not being released says, well, who are those people? I want to know who they are, and how are you saying they're similar to me? I'm different. So it's not totally transparent, and it may not be totally explicable, but this is a lot easier to explain than a random forest or gradient-boosted trees, and it's certainly going to be a heck of a lot easier than a big neural net. So there are a lot of virtues to nearest neighbors. As I mentioned, you can begin to run into memory and time issues as the amount of data increases, but still, unless you're dealing with really, really big data, nearest neighbors works pretty darned well. Thanks.